Here's the models you saw in class for a reaction that has an energy barrier. That energy barrier will prevent reaction unless molecules have enough energy to go over the top. This temperature of 25 degrees C results in no productive reaction. The molecules are unable to pass the barrier. If I raise the temperature, then the molecules initially have more energy and therefore can go higher up on this barrier, but still no productive reaction here for that molecule. If I raise the temperature high enough, the reactant molecules can have enough energy to get over the barrier, leading to a productive reaction. A productive reaction requires molecules to surmount the energy barrier. Here we now have a catalyst that comes in and lowers the energy barrier. And now, even at this low temperature, a productive reaction can occur. We'll watch that again. Here's the energy barrier, nice and tall, but a catalyst will lower the energy barrier, making it possible for molecules to pass even at a low temperature. So reactions can occur at lower temperatures than they ordinarily would. Here I'm showing you a realistic example of a catalyst. This is a contact lens cleaner that contains hydrogen peroxide. This is the chamber in which I disinfect my contact lenses. It has a place here to snap a lens in and another place to snap another lens in. And on the bottom it has a catalytic disc. I'm putting the peroxide-based cleaner in the vial here. And if I add the catalytic disc, when I add the catalytic disc, then a reaction begins on the surface of the catalyst. Here you can see numerous bubbles appearing on the surface of the catalyst. So that is the decomposition of the peroxide. Those bubbles are oxygen gas. Hydrogen peroxide is thermodynamically unstable, so it's at a higher potential energy than water and oxygen gas, which can be produced by its decomposition. Originally, without the catalyst, there's a high activation energy, a high energy barrier. So without the catalyst, nothing is happening. The catalyst opens a new pathway that has a lower activation energy. So now at room temperature, the reaction is going. I'm going to remove the catalyst, and you can see that the reaction stops. The reaction only occurs when catalyst touches peroxide. If I reinstate the catalyst, bubbles once again immediately appear. The catalyst itself is not destroyed in this process. I can reuse this catalytic disc over hundreds of uses, hundreds of days, and it will still function to catalyze the decomposition of hydrogen peroxide. So this is one of the great benefits of a catalyst. It is reusable, infinitely reusable. Without the catalyst, it's possible I could get the peroxide to decompose by heating it. With a high enough temperature, I could get the molecules to overcome this energy barrier and turn into water and oxygen gas. However, the catalyst makes this reaction go at room temperature. It's much more convenient. Since the catalyst is never destroyed, that makes it very convenient. It'll take a couple hours for all the peroxide to be decomposed. The benefit of this system is that if I were to put peroxide in my eye, it hurts tremendously. However, after all the peroxide is turned into water, it will not hurt my eyes at all. Peroxide is a great disinfecting agent. It kills bacteria. Since I want my lenses to be clean and sterile for the next day, this is a great system for doing that. All right, here the first question asks you to sketch the catalytic system. So make some kind of sketch from what you've seen. And there's this area where you put your actual lenses, and then there's the catalytic disc down here. And we can label that as the catalyst. And you saw that the bubbles form on the catalyst. So put some bubbles in your picture. The catalyst allows the decomposition of H2O2, the hydrogen peroxide of H2O2, to occur at room temperature. So the actual reaction is the H2O2, actually two of them, turning into two molecules of water, which remain in the vial, and oxygen gas that bubbles out. And the importance of this is H2O2 is a good disinfectant, but it is also very painful to put in the eye. So you want to decompose it so that it turns into water, which is harmless for your eyes. EYES, exclamation point. Okay, so something like that is a reasonable summary of the catalytic system. The other important note is that catalyst is good for hundreds of uses. Hundreds of uses. So that's a key concept, that the catalyst is never consumed, it's not used up, it's good again and again and again and again. Alright, now 2 has this interesting diagram. I'm hoping this looks to you like a mountain. You can see we have reactants here in the middle and products here. So this is very much like the interactive physics simulations. This is the uncatalyzed pathway here. It's a high mountain, large energy barrier, meaning at room temperature this is a very difficult. It is unlikely that molecules will have enough energy to get over this hill, and so therefore there may not be any reaction. If there is a reaction, it may be very slow because only a few molecules out of a population will have enough energy to surmount this barrier. So maybe it's 3 molecules per hour can react. You can see that this is the interesting part here. I'm hoping this looks to you like a little road. It's an alternative pathway. And I'm hoping it looks like a very nice, easy pathway, gradually sloping. It ends up at the same place. It takes you from your reactants to your products, but using an alternative pathway. Molecules that meet the catalyst can take this alternative. By meet, I mean contact. Contact the catalyst can take this alternative pathway. In the reaction you just saw in the contact lens vial, those molecules that touched that reactive surface, that catalytic surface, started bubbling, meaning molecules were taking that pathway because the catalytic surface allowed them to do so. Without the catalyst, this pathway was not open. It didn't exist. You can think maybe of the catalyst as a guide, knows a special way. So this is a metaphor, but it's a reasonable metaphor. It's a model. knows a secret way to get from this valley to this valley. And so the people who meet the guide are able to take that nice, easy pathway to get there. Those that don't meet the guide only know this very difficult pathway over the top of the mountain. So less energy, and I'll call that activation energy, is needed in the catalyzed pathway. Why don't I write it this way? Needed to take the catalyzed pathway. So in a population of molecules, this very difficult pathway might be only 1 in 1,000 or 1 in a million molecules has enough energy to do that. Whereas if the activation energy, the energy barrier here, is small, then maybe a very large fraction of the molecules in the population are able to get to products. If we talk about human populations, mountain climbers could do this. Mountain climbers could go over the top of this high mountain. But mountain climbers are very rare in the population, whereas this would be like the paved route, wheelchair accessible. Anybody can do this pathway here, the catalyzed pathway, and that's a reasonable way of looking at a catalytic pathway. In your rocket lab, you'll use hydrogen peroxide to generate oxygen gas. The equation for that reaction, we've written it once above. You might not need to write it again, but I'll write it here so you can see it. 2 hydrogen peroxide molecules turn into 2 water molecules and oxygen gas. That reaction can be catalyzed by ions in solution, aqueous ions. You'll use potassium iodide as the salt that provides the iodide ions. I wanted to show you a possible mechanism for how it works. If you recall, molecules have to meet the catalyst. So here's the catalyst right here. Here's a reactant, a hydrogen peroxide molecule. If the peroxide meets the catalyst, then some reactions can occur. It's not a magical transformation into water and oxygen all in one step. But this should seem reasonable to you. The iodide could react and split up the peroxide into basically 2 halves. There's the iodide right there. Then this OH over here could react with a second peroxide, because in the equation you can see there are 2 peroxide molecules. So let's see what happens there. Sketch these products with me. All right, this OH could take, for example, this hydrogen. And if it did, then you've got a water, which is one of the products of the reaction. Water is a product. So we made a product. What's left over? There'll still be this OOH part here. OOH. And there will be a negative charge here, so I'm circling that. All right, so we've made our first product. We reacted 2 peroxide molecules. Carry this molecule over. So here's the OOH with a negative coming over here. And perhaps it could react with this molecule up here. So take that molecule here, take this molecule here, have those 2 react. We could make HOOI. So this O could end up bonded to this I. That would leave you with an OH with a minus. Now, these molecules here are perfectly
arranged to make further products. So this OH here needs an H to form water. Well, here's an H. So we could take away that H and form HOH. Then you'd be left with this O, O, and an I. And the OO could form a double bond. So these two O's here could end up with a double bond. But in order to do so, they'd have to kick out this I, which would be the I minus. You can see, I hope, that here's the catalyst regenerated. A catalyst can't be destroyed or used up. Here it is, ready to start this process all over again by reacting with another peroxide molecule. If you look, you should see here's a reactant. Here's the second peroxide molecule. They didn't really react with each other directly. The catalyst allowed these intermediates to form, which then go on and do lots of reactions. But the overall products are, here's a water produced here, here's another water produced here, here's an oxygen gas produced here. So these two peroxide molecules circled in red turned into these three products circled in green. All the other molecules are intermediates that get used in future reactions. This OH gets used here. This HOI gets used here. This OOH gets used here. This OH reacts to form products. So I'm hoping this has meaning to you. I know it's complicated, but the idea that the catalyst interacts with molecules to form these intermediates, that's the usual way catalysts work. And at the very end, the catalyst will be regenerated so it can start the cycle all over again. If you imagine the catalyst as a guide, it guided this molecule through this complicated pathway and then said, you're done, I have delivered you to your destination, I'll go back and guide the next molecule.